These notes are for AP Calculus AB. This is 9.4a on evaluating limits with L'Hopital's rule. L'Hopital's rule, again, is only for evaluating limits, and I keep pointing this out because it involves derivatives, and you don't want to mix it up with taking a derivative. So it says if you have a limit of a function divided by a function that has an indeterminate value, and indeterminate values are of the form 0 over 0 or infinity over infinity, then that limit is equal to the limit of the derivative of the numerator divided by the derivative of the denominator. Do not mix this up with quotient rule. So quotient rule, of course, is used for taking the derivative of a function written as a fraction. This is L'Hopital's rule, which is used to evaluate a limit. And you have to know derivatives in order to use this. So it's simply taking the derivative of the top and the bottom, and then you reevaluate. If you're still coming up with an indeterminate form, you would take the derivative of each again. You would just, again, apply L'Hopital's rule and then try to evaluate once more. So these work with limits approaching numbers as well as limits approaching infinity. As long as you have that indeterminate form, you can apply this rule here. So I have lots of examples to go over with you. All right, so we'll start with the limit as x approaches 0 of sine x over x. This is actually a special trig limit that we learned at the beginning of the year, and you were just supposed to memorize that its value was 1. Well, if you don't have it memorized, L'Hopital's rule will tell you this value. So notice, if we try to direct substitute 0 in for x, we're going to end up with sine 0, which is 0, divided by 0. So that's my indeterminate form, 0 over 0. So I can apply L'Hopital's rule. So this is equivalent to using L'Hopital, the limit as x approaches 0 of the derivative of sine, cosine, over the derivative of x, which is 1. So now try evaluating again. And when I do, I plug in 0 for x. I end up with cosine 0 divided by 1, and cosine 0 is 1. So 1 divided by 1 is 1. So there's that answer without having to have the value or that special trig limit memorized. Okay. All right, so this one here, if we plug in 0 for x, we end up with e to the power 0 is 1. 1 minus 1 is 0. Plugging in 0 to the denominator also gives us 0. So we have that indeterminate form, 0 over 0, and we can apply L'Hopital's rule, which says to keep your limit, take the derivative of the numerator. So derivative of e to the 2x is e to the 2x times 2 minus 0, and divided by the derivative of x, which is 1. So now we should be able to safely plug in 0 here. We get 2e to the power 0 is 2 times 1, or 2. All right, this one says the limit as x goes to infinity. Now, with infinite limits, you can use your shortcut of comparing top to bottom highest powers, but maybe we're not always really good at that. This one is natural log x squared divided by x squared, and in comparing the two. So if you can remember the graphs, this one's pretty easy to see. It's simply comparing the rate of growth as time goes on. Which one's faster? So you might consider rewriting ln x squared as 2 ln x over x squared. So remember how natural logs or logs grow very slowly while x squared is going to grow faster. And so my quadratic will always grow faster than a natural log function. And so this one should be bottom heavy with an answer of 0. But let's go ahead and verify this with L'Hopital's rule. So if I want to plug in infinity or a really big number, natural log of a very big number is a very big number. And if I plug in a very big number here and square it, again, I get a very big number. So this is just the indeterminate form, infinity over infinity, in which case we can apply L'Hopital's rule. So we have now the limit as x approaches infinity. And we'll take the derivative of the top. So I have 2 times the derivative of ln x, which is 1 over x. And in the denominator, the derivative of x squared, which is 2x. If we plug in our very big number now, 2 divided by a very big number becomes 0. 2 times a very big number is a very big number. This is not indeterminate. Only infinity over infinity or 0 over 0. They have to match. 0 over a very big number. So this is a bottom heavy limit. So you'll notice it show up as a bottom heavy limit at some point. You could also just continue to reduce your fraction a little bit more if you wanted. So you have 2 over x divided by 2x. And instead of dividing by 2x, we could multiply by the reciprocal 1 over 2x. So you'll see you end up with 1 over x squared, which is definitely easy to see that it is bottom heavy. So eventually, here or at the end, or maybe you noticed it way back here at the beginning, that it was a bottom heavy limit. And the answer then is 0. All right, so with this one, same idea. It's a limit at infinity, and you might just compare the rates of growth of the 2 functions. Exponential growth functions are always faster than polynomials as time goes on. And so this one should also be bottom heavy and give us an answer of 0. So we're going to verify using L'Hopital's rule. So first of all, if I plug in a very big number, infinity, we're just going to have a very big number cubed plus 2 times a very big number is a very big number. E to the power of a very big number is a very big number. So it is indeterminate, and it's only when it's indeterminate that you can use L'Hopital. So you want to be really careful that you don't accidentally apply L'Hopital's rule when it does not apply. You could get a false answer from it is all. So here, we bring this over. We'll take the derivative in the numerator, 3x squared plus 2 over e to the 2x times 2. So again, from here, if we evaluate again with a very big number plugged into both, you'll see that you still have infinity over infinity. So we'll apply L'Hopital's rule again. And there's all limit problems. So you have to keep this limit condition going until you evaluate the limit, just like you learned to do at the beginning of the year. So in the numerator here, 6x. In the denominator, e to the 2x times 2 again. Okay. So I could reduce here, but that's not necessary to do. If I plug in a big number, it's still going to be a very big number divided by a very big number. So we're going to do L'Hopital's rule again. So here we get 6 divided by e to the 2x times 2 again, 8. And again, I don't need to bother with reducing. It's really just comparing this value. A limit at infinity, I should get an answer here. You can see that the top is going to stay as 6. The bottom will get really, really big. So this is a bottom heavy limit. And so my answer is going to be 0. All right, so here is the limit at a constant, and it's not 0 or infinity, so I wanted to make sure you saw a different case. If I plug in pi over 2, we get pi over 2 minus pi over 2 is 0, and tangent of 0 is 0. So you will get 0 divided by 0 here. That indeterminate form tells us we can use L'Hopital's rule. So we'll keep our limit as x approaches pi over 2. And in the numerator, the derivative of tangent is secant squared. We'll keep pi over 2 minus x. And then follow up with the derivative of what's inside. So the derivative of inside here is -1. In the denominator, the derivative here is just 1. So this should hopefully simplify right here. We just need to plug in pi over 2. That is going to give us secant squared 0 times -1. And then multiply by -1. So secant, or the reciprocal of cosine. So cosine of 0 is 1. Secant is the reciprocal, which is also 1. 1 squared times -1 is -1. All right, last problem. So this one does say -infinity of x squared times e to the x. You'll notice that this is not written as a fraction of f of x divided by g of x, which means we have to rewrite it that way to see if it is in that indeterminate form. So how do I know which one to move? E is always safest to move rather than moving a polynomial or algebraic piece down. We want to move the transcendental function down to the denominator. So we're going to rewrite it first. So x squared over e to the -x. So again, you could figure this out pretty easily by comparing the rates of growth of the function, but it is approaching -infinity. So when I square that, you do end up with a very big number. Over here, e to the power of the opposite of x, so the opposite of -infinity is +infinity. E to the power of a very big number is a very big number. So it's really comparing whose rate of growth is faster. And again, that exponential is going to have that faster rate of growth. So my answer should be 0, but we're going to verify using L'Hopital's rule. So on top, 2x. In the denominator, -e to the -x. Okay, so again, if we plug in our -infinity or a very big negative number, we end up with a very big negative number on the top and a very big negative number. This -infinity over -infinity also counts as indeterminate. And so we can continue again with L'Hopital's rule. So let's do that again here. So the top derivative of 2x is 2. And on the bottom, we get back to positive e to the -x. So you end up with a finite value over e to the power of a very big number, infinite. So again, bottom heavy, and my bottom heavy limits at infinity are always 0. All right. So you've seen now how to use L'Hopital's rule for limits, not for derivative problems, but for limit problems. And this is just a really nice trick if you're having trouble evaluating a limit of the indeterminate form.